Let's begin. I want to pick up where we left off last time, and I'll remind you briefly of what we were doing, because this problem is going to be relevant for some of the things we're going to do next, and for your homework, for the exam. And if you remember, we were looking at measuring the heat distribution, or specifically the temperature distribution, in a heated rod, fixed temperatures on both sides, and some source of heating like a lighter or hair dryer, something blowing at it, something heating it in the middle, and we wanted to see how the temperature varies along the rod. Now, that's useful because we could know at different points what the temperature is. If we're studying the material, if we're studying material failure, we could estimate where, for example, the material is going to be heated most. That's going to affect its tensile strength and it's going to make it weaker and so on. So a lot of things you can draw out of this. And I mentioned this K coefficient, which measures how fast or how easy it is for heat to move through the rod. And in our code last time, we had a few parameters to tweak. We had the location of the Are we good? Right. We had the location of the heat determined by A, the spread of that heat source, and the alpha, the amplitude of the heat source. Okay. If there's any question, you guys, let me know. Okay. Yeah, thank you. So, and K told us about how fast the heat is going to be dissipated along. Last we left off, we solved this problem. We varied some of the parameters together, and we started asking some critical questions. And I want to emphasize that I'm not giving you this heat transfer problem for the sake of this heat transfer. In it, because I'm not teaching you about the problem. I teach you about how to think as an example. Vary alpha and gamma, and we were just about to vary K. What would happen to my temperature? I change one of them, fix the others. What happens to the temperature? We had some great analysis last Tuesday, with what happens with the location of the heat and conditions for sanity, etc. So if you remember our code, I'll zoom a little bit for those. And so open up those notebooks and let's run it again. We had the heat located at about 1/3, and we were working with 400. We solved the system and plotted the temperature distribution. 100 on the 300 on the right, and there was some heat in the middle. What happens to the temperature distribution? Change. What happens when you this? So what is the sensitivity distribution? Cases. What happens when K is very large? Because you at those extreme bounds. It's going to be. So that's what we're going to do next. We're going to K and however, what's our also we have what's going to happen is if K is very, very small. Or of course it's going to concentrate all of that heat in there because there's no room. So let's test this hypothesis. Okay. All right, so let's take K, let's say K equal 1. All right, so this is the current result with K equal 400. Let's take K equal 1, run it. Oh, look at that. At K equal 1, our temperature, where the heating source is 35,000 kelvins, which is unrealistic. So that tells us this model actually breaks for such small values of K. But the point being is that this is consistent with what we expected. As K gets very, very small, there's no room for the heat from the heat source to move through the rod. It's going to get concentrated and concentrated, concentrated. It's going to reach a peak of whatever temperature it wants to reach, right? And if you look at the equation, as K approaches 0, what happens to the right-hand side of this equation? It gets bigger, approaches infinity. So then the second derivative becomes infinite, so you have an infinite heating of the material, which is unphysical, but still the math, this model tells you that. Now in reality, this model is not adequate for K approaching 0. K is a function of the temperature, actually. So you have to refine this model. So this becomes a model error, a modeling error for small values of K. But still, this math shows it. This equation, this system that we solved, it does show this result that's consistent with our intuition. Okay, what happens on the other end when K approaches infinity? Or heat is distributed very, very fast through the rod. There's no resistance. Okay, from 300 to 500, you mean no peak? Okay. Okay, how is it distributed? Okay, so evenly, is it like constant? How is it 300 and 400 and 500 and constant? Okay. So what's the word there? Linear. Okay. Okay. Any other thoughts? What happens when K approaches infinity? You can think of it mathematically as well. What happens to the equation when K goes to infinity?
It's going to go to 0.
The right-hand side is going to go to 0. So then what is your resulting equation?
It's going to be d2
Mm-hmm.
second order t with respect to x is going to be 0. Yeah.
What's the answer there? T prime is a constant, and therefore T of x is Cx plus C0. Linear, exactly as your colleague said. Right? So we expect as K approaches infinity, or very large values, the source term contribution is insignificant, because whatever heat is going to transfer to the rod, it's going to be dissipated very quickly through the rod. It's going to go through the ends, 500 and 300, whatever direction it wants to go. Mathematically, this means that distribution is just going to be linear. Why? As K approaches infinity, this entire right-hand side, S over infinity, is 0. Whatever S is going to be 0. Unless S is infinity, but it's not. So then it becomes 0. So you have a second derivative equals 0. When is a second derivative equal 0 of a function? When the function is a straight line. And that's how you get the straight line for temperature. So let's verify that. Okay? So let's take a very large value for K. Say 1e to the 6. Oh, look at that. Straight line, as expected. This is just critical thinking. It's just saying, okay, asking questions. What happens here? What happens there? Does this make sense? Does this not make sense? That's the process you need to apply, not to the heat transfer problem, to every problem you're looking at. Start asking questions, even if you don't know the answer, even if they're scary. What happens when this is, even if your answer is I don't know, then you go research it a little bit. Or make a hypothesis and then go and test it. And if you're right, then it's a tremendous victory. There's no greater feeling than validating your hypothesis, saying, this is my hypothesis, I'm going to go test it, and the result is correct, then this is great news, right? Okay. So that gives you an idea of how this is actually how we think in practice, how you should think in practice. Doing research or engineering in practice, this is what you need to be like. And this distinguishes you from being a technician. I mean, even a technician does critical thinking, right? But you as an engineer, you're technician 2.0, okay? You need to elevate that thinking and be more of a critical thinker because you understand the mechanics of it. And you have math next to you. With math, it's frankly, so there's a saying that physics is harder than math. Although people think that math is harder than physics, it's the opposite. Because in math, the problem is already defined for you. You have the equation. Solve that equation. In physics, you have to come up with the equation first. How are you going to the equation? What law do you use? And then you have to solve the equation. So once you have an equation like this, it's, k goes to infinity, k goes to 0. What happens to the equation, right? Okay, it's not that hard when we're doing it together. I understand, because I'm here to guide you, etc. But it's not different than this. Don't overcomplicate it. Don't think that there's, rocket science behind it. Even in rocket science, it's not rocket science. It's just accumulated knowledge over time, and you think critically about it. Okay. So we're done with that problem. In your homework assignment, you're going to see a similar problem, and except it has something called advection. So actually, we're going to take the same rod, and we're going to blow air at it, and there's going to change the dynamics a little bit, and you're going to analyze the problem the way we analyzed it here. Okay. Now, before I jump into the last piece of linear solvers, I want to go back. So you see what we're doing with numerical methods. You're becoming an expert in the numerical methods, an expert in the coding, in the techniques, but all of those are serving one purpose, which is the engineering purpose, which is the science purpose, understanding the problem, okay? But a lot of times we get entangled in the little minutia of the details of how to solve the problem. And this is one of them, and that is the cost of this linalgebra.solve. You've heard me say over and over again that direct solvers, is this a direct solver? Yes, it's a direct solver because it's solving the system exactly. And you've heard me say and claim in the beginning of this unit that direct solvers are expensive, especially for large systems. Okay, so let's maybe get a taste of that. Okay, how can we test if this is costly, or how can we check the cost of this, right? We can run a few anecdotal experiments on this and say, okay, so I'm going to bring this back to some reasonable value, 400. Okay, and the thing that is going to determine the size of this system of equations is the number of equations, obviously, right? And that is tied in directly to this number of grid points, which is n, okay? Which is n. So my claim is that as n becomes large, the solver is going to cost more and more time, right? So with n100, okay, we ran it, and it was pretty quick. It gave us the solution quickly. If we go to n equal 1,000, and I'm doing this just kind of not very rigorously. Ideally, I would want to put a timer and time the solver, how long it takes it to solve it as I vary the number of points n. But I'm just trying to get a feel of how long this will take. So for 1,000 points, yeah, I did it pretty quickly. Let's see, Python performance. Give me a second here. I'm going to Google something. Okay. So a better way, okay. So a better way to measure this is to use a performance timer. Let me see if this is going to work. So I'm going to import something called import time. Okay, so time is a module that measures time on a computer, right? Okay. So what I'm going to do here, I'm going to do a tick-tock on this. tick is time dot time. So it's going to measure timestamp before we solve the system. And then after we solve it, I'm going to take a measurement of time. And their difference is going to be the cost, the time that we spend doing this, right? So you set your timer, and then start, stop. So tick, tock is time dot time. And then print elapsed time is equal to tock minus tick. Okay, so let's try it. Okay, 0.13 seconds, okay, for 1,000 points. So print elapsed time for n equal, say, n equal, n is, oops, okay, for n, stick tock minus tick. Okay, so elapsed time for n equal 1,000, well, it changed. It's now 0.3 seconds, right? Because we're still at small scale, 0.1, 0.2. This is very small differences, okay? Now let's go to higher. Let's go 10,000 points. Okay, 10,000 points. I'm going to run everything again and hit here. Oh, look at that. Still running with only 10,000 points, which is nothing. Okay, it's 5.5 seconds. Right, so you can see now we went from, just by multiplying by a factor of 10, we went exponentially. We were going 0.1, 0.05, 0.1, 0.3, and then 5 seconds. Now, like this, let's do 50,000. Oops. Still running here, with 50,000 points. So that's a matrix size of 50,000 square, right? It's still running. Okay. And in computer time, this is a century, right? Even if it's going to be 20 seconds or 45 seconds, it's long, right? Sitting there and waiting for it to complete, it's long. If you try it on your computer, if it crashes, then it would have reached like the limit of the capacity on your computer. Yeah. So this proves the point, right? So for large systems, which are actually, you're going to encounter large systems like this one in practice, and 50,000 points, again, is nothing. You will be talking about millions of points, millions of degrees of freedoms. To do something realistic, direct solvers are a terrible idea. And early on in the lecture slides, I showed some plots showing the exponential rise of cost. So what I did there, I ran this timer, but I varied n. So for each n, I calculated the time, and I stored that, and I plotted that versus n. And so you can do this in this case, and it's probably going to take a little bit longer. So we'll just leave it alone, let it compute in the background, and we can proceed with life. Okay, we'll let it complete. Okay. So now that sets the stage for iterative solvers. Okay. Iterative solvers, I also claimed that they are a great, cheap, and less costly alternative to direct solvers for very large systems of equations, but they have to be sparse. Yes, Ashton?
So what's, like, for data sets that you do, like, what's the average, like, number of n rows or, like, equations?
For a direct solver, to use a direct solver?
Or just, like, in general, like, what's, like, an average number of equations that you use, like, in research?
In research? It depends on the problem. Like, there's a problem we're looking at right now, and today, we're putting a proposal together on this. It's top secret, so I cannot say much. But no, it's fine. In some of the cases, I have anywhere between 400 billion degrees of freedom to 4 trillion degrees of freedom. So those are the numbers of variables. So I'm solving for x, y, z velocity, for pressure, temperature, for volume of fluid, for particles and to represent the solid, the stress tensor in the solid that has 6 variables, positions of the particles, radiation rays, etc., on a grid, and things going on. So, and that's what we want to be at today. And in 10 years, we're going to be a couple of orders of magnitude, so we're getting higher than that. So we're talking 400 trillion and so on. So that's the scale. In like state of the science research, that's the scale you're looking at. But on like an average problem we're solving every day, I probably have a couple million degrees of freedom. And so there's no way I would use a direct solver. It's out of the question. It's not even an option in our codes. Okay? Yeah. So, all right. So let's see if this Python, it's still running. Yeah, we can give up on that. Okay. So this brings us to iterative solvers, which I claimed at some point that they are faster and more efficient than direct solvers, specifically for large systems of equations. But those systems have to be sparse for iterative solvers to work effectively on them. There's a whole theory behind why that is the case. We're not going to dig into that. We're not going to learn about that. But what you care about is when you have a sparse system that is large, you immediately should think about using iterative solvers. Now, are sparse systems that prevalent? Absolutely. In everything you're doing with mass, heat, and fluid mechanics, heat transfer and mass transfer, anything that has to do with transport mechanics, which is your bread and butter as chemical engineers and process design, etc., you are going to end up with sparse systems. Take this heat transfer problem. We ended up with a sparse system. Was that tridiagonal? In 2D, it's the same thing. In 3D, it's the same thing. Okay, you have more zeros than there are non-zeros. And the same thing when you do it for fluid mechanics, when you do it for mass transfer, and all sorts of things. Okay? So sparse systems are prevalent. They're going to be large. We should be using iterative solvers. That's the conclusion. Okay. Now, compared to direct the idea behind iterative solvers, let me just explain this concept here first, is that instead of trying to get to the solution exactly, we want to get to an approximate solution. And the reasoning is that, one, that's faster. Second, we already have modeled the heck out of our system. We have so many approximations already made on the system. One more approximation is not going to make a big difference. Solving the approximations exactly is not going to improve our precision, right? It's not going to improve, our accuracy, because that accuracy has already been embedded in the model itself. Okay? So the truth. So if the model is pointing to the truth, let's just keep pointing to the truth. Okay? So no amount of precision is going to make up for accuracy, for lack of accuracy. So the idea is like we've already started doing approximations. This heat transfer equation is an approximation to reality. So why do I need to solve that approximation exactly? Why not solve it approximately? And that's the idea of iterative solvers. We start with a guess for the solution. How do you start with the guess? I don't know. Maybe we take the average temperature for this problem. If the rod is at 500 and 300, maybe the average temperature is going to be 400. So we're going to guess that the solution is 400, and it's going to converge to the correct solution. Okay? It's going to be just fine. Then, after we guess the solution, we're going to come up with a recipe, okay? A recipe from the governing equations. We're going to come up with a recipe to improve that guess. So we improve it one time and use the new guess, the new solution as a new guess. And then keep improving it until we say we are happy or satisfied. How we're going to define that, we'll see. Okay. So iterative solvers, like I said, they are more efficient, faster for large sparse systems. We use them, obviously, when it's faster to solve iteratively than directly, but it's particularly important that they are used on a sparse system that is diagonally dominant. Okay? So diagonal dominance means that for each row in the equation, so take row 1, row 2, for each row, go through each row, the diagonal entry, the value on the diagonal entry, AII, right? So A11, A22, A33, etc. In the magnitude of the value in the diagonal entry is greater than or equal than the sum of all the off-diagonal entries in absolute value. So you pick a row, look at the diagonal entry. Is it larger or equal than the sum of the off-diagonal entries? If it is, then it's for each row, then it is diagonally dominant. Okay? And a system that is not diagonally dominant will kill an iterative method. Again, luckily, fluids, heat, mass transfer, the things we do in chemical engineering always result in diagonally dominant systems. Okay, so that's not something you need to worry about. However, if it's not diagonally dominant, oftentimes what you could do is something called pivoting. You rearrange the order of the variables and the equations. Okay, let's see how that would work. Okay. There are two ways of pivoting. This process is called pivoting, of rearranging the equations. You can arrange the order of the equations or the order of the variables. So let's start with this example. These are three equations and three unknowns, right? Equation 1 is 0x1 plus x2 plus 3x3. And then equation 2, 0x1, 2x2 plus x3, and so on. Okay? Now you look at this equation. In the first equation, the main diagonal entry is 0. The off-diagonal are 1 and 3. So 0 is not greater than 1 plus 3. So therefore, we know that the first equation were not diagonally dominant, at least in the first equation. Equation 2, 2 is on the main diagonal. It's greater than 0 plus 1. So we're good. Equation 2 is diagonally dominant. The third equation, 2 on the main diagonal, is not greater than 1 plus 4. So in general, this system, most of the equations are not diagonally dominant. So this system is not going to be good for an iterative method. Okay? Forget about sparsity. I'm just talking about diagonal dominance. So what you could do here is if you take those two equations and simply swap them. Just swap them. If you put the last equation at the top, then 4 ends up on the main diagonal, and it's greater than 1 plus 2. And 3 ends up on the main diagonal at the bottom, and it's greater than 1 plus 0. But what you've done here, you've rearranged the order of your equations. So your right-hand side, B3 is B1 and B3, they get swapped. Okay? That's called row pivoting or equation pivoting. You just change the order of the equations. Okay? And it's easier to do it on the matrix rather than looking at the equations themselves, because with the matrix you can reason about the diagonal and look at it and visualize it. There's also column pivoting where you arrange the unknowns. So in column pivoting, instead of swapping the rows, you swap the columns. So if you look at these two columns, if we swap them, then we get diagonal dominance. Okay? So when you swap them, you need to swap the order of the unknowns. Okay? Because you've changed now which is multiplying x3, which number is multiplying x2 and x1. So when you swap them now, they became diagonally dominant. 3 is greater than 1 plus 0, 2 is greater than 1 plus 0, and 4 is greater than 1 plus 2. Okay? But you have to remember to swap the variables as well. So column pivoting, you have to swap the unknowns. Row pivoting, you have to swap the right-hand side. Okay? But write it in matrix form first. Now again, this is rarely the case for these large systems. Okay? And the systems we deal with in chemical engineering, so you don't worry about that. I've never had to do pivoting in my entire career. I've never had to worry about that, because all our systems are diagonally dominant. Even if one equation is not diagonally dominant, we don't worry about that. The system will just work, and the iterative method will work. All right, our first iterative solver, sorry, I have my back towards you, let me turn. Our first iterative is simple for historical. Nobody practice, it is the least efficient iterative solver. So it's better than direct solvers, but it is the worst in the world of iterative solvers. But it is so easy to comprehend and to reason about how these iterative methods work. We will start with this one. and try to do an example in class together and see how we can improve it a little bit. Okay. Focus with me because I'm going to introduce you to the concept of iteration today, which we will use when we deal with nonlinear solvers. So this is not only going to be helpful for the iterative method itself, it's going to be helpful for how we solve nonlinear equations. The idea of iteration. All right. So a single linear, you know that you can very easily and quickly solve for the unknown x, and you say x equal b over a. Okay? So you solve that one equation for that one unknown. Now what if you have two equations and two unknowns? I'm presenting them here as a11 x1 plus a12 x2 equal b1, a21 x. And b2. So now you have two equations, and I know you can do it by hand, but I'm not wanting to do it for two equations. I want to do it for a million equations. But I'm using the two equations as an example of how we can develop the idea of iteration. Okay? All right. So what if solve equation 1 for unknown 1 and solve equation 2 for unknown 2? See. So if you want to solve equation 1 for unknown 1, we're going to leave unknown 1 on the left-hand side, or in other words, x1, and move everything to the right-hand side. So that would make x1 equal 1 over a11, right? You do the math, b1 minus a12 x2, fine. And let's solve equation 2 for unknown 2, or solve equation 2 for x2. So we solve equation 2 for x2. So it looks a little bit similar, but you got different numbers. But then you say, but what the heck, Dr. Saad? There's x1, x2, and x1 on the right-hand side. Like, this is tautological. What? You didn't do anything here. You just rewrote the same equations, but put things on the right side. But I cannot solve for x1 without knowing x2, and I cannot solve for x2 without knowing this equation. If I plug x2 over here, it's going to give me x1 equal x1. It doesn't make sense at all. You're right. Here, I'm doing numerical methods and approximation theory. So yes, indeed, we need values for x2 and x1. Instead of doing this tautological discussion, suppose we use guesses for x1 and x2. Suppose we start with a guess for x1 and a guess for x2, and put it on the right-hand side, and use this formula to get a new value for x1 and x2. What would that do? Because we are using the true equations of the system, do this and keep doing it over and over again, you are going to converge to the true solution. So you start with an initial guess. Let's call them x1 guess 0 and x2 guess. So that's the first guess. This x2 is only an improvement on x1. Let's give it a counter. Let's call it x2 1 and x1 1. See what I did? I'm going to start here, put it on the right-hand side. I'm going to improve the tests, improve value. Then what should I'm going to take this x1 1 and x2 1, use those as my improved guesses. Put them again in the equation and repeat. So take x1 x2 1 and put them in the equations, the same equations, and then improve the guess again. Now see that counter in the superscript goes from 1, 2, 3, 4, and so on and so forth. Keep repeating until in general 4. on the previous value. So this whole thing you can calculate. And this whole thing you can calculate, you have values for. Keep repeating it. So k equals 0. It's going to be your initial guess, that's the value that you choose. You choose 0. And then the other thing, and repeat. It turns out that this is a much faster than a direct formula. It's much important, this idea here that we just did. We took an equation that was kind of implicitly or on and split everything depend you know, everything on the left will be our new knowledge, new updated value. So we're going to repeat that process. The procedure is called iteration. You keep iterating until you get to the answer. Okay? So let's take an example, and if you want to do this by hand, grab a pen and just do a couple of iterations. You do this once, you get the aha moment. Okay? So grab a pen and paper and do it with me on the board. So I'm going to take two equations and two same as before. And so this is a system of equations for x1 equal 10 and x1 plus 5x2 equals 15. And the true answer is 0.47 and 0.7. Okay? This is the true solution. Okay? This is the exact solution. For our iterative method, what I want to do, okay, hold on. And that's going to be our formula for the update. An initial guess is 0, 0. So x1 is 0, x2 iteration. First iteration is equal to 0. Give us the first at k equals 0. You have x1, x2 equal here and x1 is 0 here from that equation. And you compute the new updated value. Okay? So by hand that equation and then one more iteration after that. Okay? Try, turn on the light. K equals 0 and go on to the value for get the second operation. You can write the equations in traditional form if you want, and not the matrix form if you want. Just use the formula on the upper right. You have to just keep track of which value you're using. as your message. What's the only thing that's changing in this next game, right? Nothing, they're not changing. Everything is there from the original equation, right? Here you this yep, one. We'll talk about that later. Yeah. We were just doing a couple iterations, right? Yeah. But you can't separate them. You have to do them in one step because yeah, it's cross. Yep. Eventually it will oscillate a little bit and it will converge. Yeah. And you repeat on the second iteration, right? Okay. So, there was an aha moment. If you didn't get it yet, or you get from the calculation, you need to get it. Because once you get it, this temperature here is not an exponent, it's not a power. Okay? It's not an exponent. Be a solve x1 altogether separately from x2. That's not even a system anymore. It becomes a single equation. Okay? Now, I do it this way. With my k, I put my x1, x2, so x1 x1 0 that k. When you next iteration, a equal 1, x1 2 from this guy, that guy, and it depends on the previous ones, right? Then you propagate the tail. Now what happens? The exact function is 0.4 and 0.7. You see 0.4, 0.6, 0.5. We oscillate a little bit, and then we start merging. Then, in 100 iterations, we get 0.4. We got most of the significant. 6 we got 2.705. Because it does converge. Because that the governing equation. Solution. That as we get the solution in the black hole. We're going to move step by step, but turns out to be if you thought this was hard, wait until you generalize. Obviously, we're not going to use this for a 2 by 2 system. We're going to use it for a million. Generalize this. If for an arbitrary size, n by n, n is n node. The idea is still the same. Equation 1 for x2, equation 3 for x3, equation same idea. More unknowns now. You see how for any row I in the matrix, any known I in the matrix, the formula is the same. It's 1 over the diagonal entry times di. So if I want it's the same formula. Okay, this is it's equal 1 over ai minus diagonal entry to the right hand side, and here represents all the by all the previous iteration values. If you go to the right hand side over here, these are all the other terms, okay, not at k but at k. Okay? Go to the previous equation. It's the same a2, x2, a21, x1, all the off diagonal entries. Okay. General formula. Right? Now, and I'm going to give you the code for this. We're going to work together in class on it, and for the homework, a code that you can just call and use. But I want you to still be exposed to and just to see. Now, programmatically, if I'm doing this summation of summation A, J, K, that's really complicated. And then there's no thing in the same I different than J. I different than J means all the entries that are not diagonal. If I equal J, diagonal entry. It's AI, A1, A2, 2, A3. So here we're saying we want to conduct this summation, this product, for all the off diagonal entries. And the fact that there is I different than J will require that you put an if statement in your for loop. Because that's something, the product things, you're probably going to have to do it with a for loop. Or I and J going all the way, multiply by xjk, except for when I equal J. You're going to have an if statement for every J combination. You're going to check if I is different than J, then that term. And if statement is going to kill your for loop, that makes it tremendously inefficient. No, there's a lot we do. We modify this equation by adding and subtracting I term. So what happens, I keep this summation as if it's the full product. So I add an AII xj, okay, and subtract it at the same time. So what happens when you subtract it, AII over AII becomes 1. So you inherit an xij over here. This summation doesn't have an I equal J. Mathematically, these are identical. Numerically, they're very identical. There might be some round off, but it's insignificant. But I like this because it stresses the fact that the new iteration for the ith variable, the new iteration k plus 1 for the ith variable, is equal to the old iteration plus subtraction. That's the idea of the iterative method. Start with a little bit more sense that it's a correction made to an incorrect guess. That correction is based on the governing equations. That's why it converges. This correction didn't come from Mars. From the governing equations. But this form is really nice because the previous form is like this obscure form that just k plus 1 is something. K plus 1 is equal to xk, the value has the fraction. And then you keep reusing. The loop over k, this is not a power, so I forgot the parentheses there. These are not powers. This is a count. This formula is meant to be repeated. Your colleague said, think of the iterations as okay, then generation 1, you prove that so k equals 0, you compute x1, and then k equal 1, you compute x2, and you keep repeating and repeating. So the algorithm looks like this. You start with a guess, or you supply a guess, you update the guess for each xi, starting with I equals 0 according to this formula, and then you keep repeating this step. So I know it looks quite complicated, but we're going to put it in a code together. I'm giving you a code here. I have a bunch of codes also that will be supplied in the homework. And we're going to write the code together in class, whichever one you want to use in the homework or in life. If you want to write your own, that's fine. I'm happy either way. Okay. So let's go ahead and do this example together in class. It's a very small system. 3 by 3, okay, and it's given by this formula, these equations up there. We're going to start with an initial guess of 1, 1, 1, and the exact solution is this guy, 0.3, 3.04, and 2.30, and we're going to actually implement the Jacobi method together. Now, why am I doing this? Because I want to expose you more to coding. Okay? In previous years, when this was taught in the spring, this group had experience, so we skipped that coding exercise. But years before, this used to be a homework assignment. Like you code it, you go figure it out. Okay, so it's not as hard as it used to be. Okay, but at least we're doing it together. And let's go ahead and get some Jupyter notebooks up and running. And this is coding activity, let's say 3. So we'll make a new notebook here. 3. And here. Okay. Now let's look at the Jacobi algorithm. Implement that formula. Okay, so that's our formula over here. I figured that it's a little bit more involved, this code, but we can just work on it together. So I want this algorithm to be a standalone routine. I want to be able to call it, and I want it to return an answer to me. So when you're sitting there trying to design a routine that people can use, the first thing you think about is that routine is going to be a black box to everyone using it. What they need to know is what inputs they need to provide, what outputs to expect. So what inputs do we need? Pardon me? The matrix, minimum, right? Because we need a system of equations, right? But the matrix is a way of applying that. So that gives us the coefficient matrix. Okay, so what else do we need? Right-hand side, okay. I'll give credit to both of you. Okay. Yes. Guesses, okay, good. What else? Anything else? Ah, that's a very, very good answer. Okay. So when to stop iterating? How do we tell when to stop iterating? At least right now. Okay, so provide a maximum number of iterations. Okay? All right, this is good. Okay. So what do you want to call it? Jacobi. Okay, fine. When I'm writing the interface, I'm just going to put placeholders there. Okay, and then figure out what they mean or correct them later as the code evolves. So we're going to put A, B. Why? Because numpy.algebra.solve has A, B, right? So I want to be consistent with that, put them in that order. But because this is an iterative solver, I'm going to need guesses, and I make sure to put guesses that this is not a single guess. There's going to be as many guesses as there are unknowns. If you have 50 unknowns, you need 50 guesses. Those are the initial guesses. And okay. So do this. Array A. So suppose someone sent A as a list of lists. They didn't convert it into a NumPy. Then internally you convert it. If it's already a NumPy array, another NumPy array application is not going to do anything to it. Okay, so this just makes sure that, and you don't have to do this, but if you're already assuming that A is a NumPy array, that's great. Don't worry about it. Okay. So maybe A is a NumPy array. Okay. About this equation here. What do I need? I need to know my location in the matrix. So in other words, I and J, right? And we said I are the rows and J are the column. A, R, C, arc. So we need R and C, the rows and the columns. Okay, and we're going to go according to this formula per row, because I is the row, right? So the variable on the ith row is equal to a bunch of things. Okay, so our loop is going to contain this loop over the rows, but we also need to loop over the columns, okay? Because we need to do that summation over there, right? Okay. So let's go ahead and do that. Okay. Okay. So how do we get the number of rows and the number of columns? If you call, there's a little utility in NumPy arrays, and suppose I have A equal, let's build this matrix here. Okay, what is it? It's 5, 1, 1, 2, 0, 0, 4. Suppose A, right? And we have 2, 3, 0. And then we have 3, 0, 4. Come on, 3, 0, 4. This an NumPy array from the get-go. A.shape is going to give me the shape of that array. You can do this for 1D arrays, 2D arrays, whatever. Okay? Now, we're using a 2D array as a matrix to represent a matrix. But A is not technically a matrix in Python. It's just a two-dimensional array. But we're using it to represent a matrix. Okay? So it's 3 by 3. And then we can benefit from this function to get the number of rows and number of columns. All right? So I'm going to do nr nc is equal to A.shape. So if I do this here, okay, nr nc, number of rows, is equal to A.shape, then print, say nr, is equal to nc is equal, it is 3 and 3 indeed. Okay, so doing it this way is going to give us number of rows and number of columns. Now here you could do an error check. You could say if nr is not equal to nc, throw an error, because you cannot invert a matrix that's not square. You cannot invert a system that's over or underdetermined. Okay, so you can do an error check here if you want. Okay, so my thinking here, I don't know what I'm going to put here yet, but I'm going to say that while my k is less than max iter, okay, or less than or equal or whatever, less than. So then, where do I get k from? I need to declare an iteration counter. So I declare it. I say k is equal to 0. That's my iteration counter. Okay. Now what this is saying is, as long as k is less than the maximum number of iterations, keep doing something. That's what the while loop does. Okay. It has an embedded if statement. And then I'm building that loop from the out to the inside rather than the inside out. I'm building it from the outside to the inside, because I'm going to keep iterating until I hit maximum iterations. All right. For each iteration, I need to do the Jacobi solution. Okay. Are we ready to do that? Right. So this was our algorithm, navigator. This is our xi is, so it's looping over the rows. So I need to loop over the rows. So loop over rows starting from 0. Okay. So then for row counter, the row in 0 to number of rows. Do the right? Okay. Does that make sense? In our outer while loop, we're going to the Jacobi formula up until we reach max iterations. For each iteration k, we need to do the Jacobi formula. The Jacobi formula asks us to loop over all the unknowns, over all the rows. For each row, solve for the unknown corresponding to that. So in other words, what this is saying is that x for the row, okay, I'm just putting this as a placeholder for a second. X row is equal to this formula, the old value plus 1 over the diagonal and a bunch of other things here. Okay, so let's think about that. I need to store my solution somewhere. I don't have any placeholder for my solution. So even if I did here x row, what the heck is x? I haven't declared it. And if you run it, it's going to throw an error and you're going to panic. Well, because you haven't declared what x is. Or so what I'm going to call it solve for solution. I'm going to declare it as numpy.zeros array of size nr or nc. It doesn't matter. I have as many unknown or solution variables as there are rows and columns. Okay? That makes sense? So I'm creating an empty or an array of zeros to store my solution in it. Solution at 0 is going to be the first equation, solution for the first equation, second equation, and so on. So therefore, over here, I can do sol at given row. So row over here is my I over here. Okay? I use the word row to enforce that this is I is not just some meaningless number. It is the corresponds to the row in the matrix. Okay? So the solution for the variable corresponding to this row is equal to, okay, so on the right-hand side, I have the old value of the solution plus a bunch of things. Okay, so let's put the placeholder here for a second, put old value, okay, or previous value, okay, for a second, plus I want to get this sorted out first. This 1 over AII is very simple. It's 1.0 over the entry AII in the matrix, in the array. And this is how you access it. It's actually not AII, a row. Right? Okay. Times, so that's 1 over AII in our algorithm, times this guy, BI, which corresponds to the row. So B at the corresponding row. Okay, good. Minus this whole thing. Minus this whole thing. Okay. So now, what is this thing? Sum Aij xj k, or sum Aij xj. You have fixed I over here. So I is fixed. And you're only summing over j. J is the column. So what you're doing here, you're taking all the entries in row I and multiplying them by all the entries in the guess. So it's actually a dot product between two vectors. The vector containing the coefficients on row I, so A11, A12, let's say I is 3. A31, A32, A33, A34. You're multiplying all of that as a vector dot product between these guess. So you can do this summation without a for loop. You can do it as a dot product between two vectors. And we learned how to do the dot product when we did the A inverse with the at symbol. Do you remember that at symbol when we did the linear systems, when we started with direct solvers? So to grab this very effectively, instead of having a nasty for loop, I can simply grab the ith row in the matrix, which is AI or A row, and dot it with the previous value. Okay? So this at symbol does a dot product, either matrix vector product or vector vector product. Okay. So now we haven't figured out what previous value is. Okay? The previous value is. And that previous value needs to be consistent with what we're putting here. So here there's the previous value at row I, and over here all of the previous values. How are we going to do this? Well, it's pretty simple. We're initially starting with the guesses, right? With the guesses. So that's really what this is. We're going to start with the guesses, and this is guess at the corresponding row, and this one is all the guesses. But then after we're done with the iteration, right? So we came in, initially k was 0, and we used the initial guess. But once we're done with k equals 0, this guy now became our new guess. So I reinitialize my guess. After I'm done with the Jacobi formula, I reinitialize my guess and I say x guess or guesses is equal to solution dot copy. We came in, k was 0. We used the guesses, it was in guesses. Guesses is equal to what came in at k at 0. Okay. We did the first iteration. Now k is equal to was equal to 0. K is equal 1 now. And we updated our solution. Now we're going to use our new solution as the new guesses. And then we're going to come back here again. Update, and then keep repeating until k is greater than max iterations. See what I did there? So I use this variable, I reused it here, and I updated it as needed. Guesses is an array containing as many entries as there are unknowns. So that's why here I'm accessing the ith entry of guesses, indicated here by row, but over here on the dot product on the right, it's the A of x guesses. So A row gives me the entries in the row, and guesses give me the entries in the previous guess, and I dot them together, and they give me that summation. That's the dot product. And that's solved. This used to be a homework assignment. Okay? We declared the coefficient matrix. We declared the right-hand side also as an NumPy array. P dot array. And we got 10, 11, 12. Now we are ready to call Jacobi. I'm going to give you the function signature, A, B, guesses, and max iteration. Okay, so A is A, B is B. Okay, what about my guesses? I'm going to put x0 here for a second as a placeholder. I'm going to what were x0 1, 1, 1. Okay? 1, 1, 1. And then max iterations, so maybe we put 10. Then that's going to be our solution. Then we print it. We did something. Okay, let's synchronize. If you want me to scroll up a little bit. So this one is a little bit hard to see. Okay, this is better. can go on ChatGPT, hey, give me an example of a Jacobi iterative solver. If you understand it, that's great, I don't care. But you better understand what it's giving you, okay? Easier than what I presented here. There's another form of the Jacobi hand, but this is one way of doing it, and I tried to simplify it as best we can, but there are things you can sugarcoat, right? It has to be done. The biggest job here is this step, recognizing that this is a dot product. The other option would have been to do a for loop. For the ith row, you loop over all the columns and do that multiplication. But it's the same thing as this thing here. Okay, so with 10 iterations, yeah. So how about we do 100 iterations? Okay, how about we do 1,000 iterations? It's not changing. How do you choose your maximum iteration? Okay, explain. So you choose your maximum iterations based on the relative approximate error between what and what? Okay, the relative approximate error between what and what? The approximation and the current approximation, right? Okay. But how do you choose which error? You have, let's say you have 50 values. Each one is going to have its own relative approximate error, right? Because x1 is going to have a x2, x3, x4, x5, each unknown. Which one do you choose? Where's the largest? Okay. All right, so let's dig into that. So that I have what? 1 minute? Okay, 1 minute. I have 1 minute. So if you notice, so this is a table. You notice in our example, 10 iterations gave us a good answer, but then 100, 1,000 iterations. This table summarizes those answers. And you see that after a certain point, our solution is no longer improving. So it would be foolish to put a large number of iterations, whereas you can get by with a few. Think of the Taylor series. In some cases, 10 terms were enough. In some cases, 50 terms were enough. It would be foolish to do 1,000 terms across the board. Sometimes 1,000 terms is not enough. So we need a better mechanism to assess whether we are converged or not. Okay? So using a fixed number of iterations is actually inefficient. And your colleague was spot on, is that we can use something else, another measure, and he suggested the relative approximate error, which is exactly right. Another measure to tell whether we are converged or not. And again, looking at this, you notice that the error between current and previous iteration is just, the numbers are not changing. So your computer can't do any better. So why keep doing things for now? Why not stop? And he suggested we take a relative approximate error, but which one do you choose? Which relative approximate error do you choose? You have as many unknowns as the system is. So, for example, if you were to take relative error, 1 variable, 2 variable, 3, you'll have vastly different errors across the board. So after 30 iterations, the error at 1 is 10 to the minus 7, the relative error in 2 is 10 to the minus 9, and the relative error in x3 is 10 to the minus 9. Which one do you choose? Your colleague suggested we choose the worst case and hold everything accountable to that. So we choose this one, the worst case. Okay, so that's one way to do it. Next Tuesday I'll talk more about how to choose the error. The problem in choosing the worst case is that sometimes one variable will be very stubborn and will not converge like the other variables, right? And so holding the system accountable for one bad apple right? It's not going to be, so we need an aggregate measure, right? Thank you. I'll release the homework today, okay, and we'll see you on Tuesday.